Okay, so in yesterday's lecture, we learned about ion trap implementations of quantum computing. So we saw that we could encode the ground state, electronic ground state of the ion as a 0 logical qubit, and the excited state of the ion as a 1 logical qubit. And we were able to perform unitary operations on these qubits by shining lasers on them. And then we could also exploit the vibrational modes of the ions in the trap to perform 2 qubit gates. So today we're going to look at 2 different architectures. The first one is an optical implementation where we encode the quantum information into states of light. And then later on I'll talk about another implementation which consists of creating superconducting circuits. And in particular, I'm going to focus on linear optical implementations. So as I mentioned, in optical quantum computing, we use states of light. To encode our information. And for the most part, I'm going to just focus on single photon linear optical quantum computing. But when I finish with that, I'll just briefly touch on continuous variable quantum computing as well. Okay, so we're going to make use of second quantized notation where we have these operators, A and A dagger, which are the annihilation and creation operators. And these act on optical states of light. So in particular, they act on number states by reducing. So if we have an annihilation operator acting on an n particle state, so this is going to be an n photon state, then we're going to reduce the photon number by 1, and we get a coefficient out the front of square root of n. And also we can have the creation operator acting on n, and we increase the photon number n plus 1. And then another useful thing to know also is that there is this operator called the number operator, which is given by A dagger A. And so let's say number operator. And that operator is the eigenstate. It's the n photon Fock state is the eigenstate of the number operator. So it just gives us the same state with eigenvalue n, where n is the photon number. Okay, so using single photons for quantum computation has a few advantages. One of them is that we can perform computation and communication in the same framework. So our qubits are going to be photons, and then we can also send these photons from A to B. So we don't really have to try and convert between 2 different physical systems. And then the other advantage is that coherence times or decoherence times for photons are extremely long. Like, there have been experiments done between 2 different islands. I think one of them was Tenerife. So they were sending photons between telescopes on, islands that were hundreds of kilometers away from each other. And these photons just stay coherent for the most part. Excuse me. So using optics, we can straight away just kind of for free, we can satisfy 3 of the DiVincenzo criteria. So 3 is the decoherence times, and then these 2 are the communication ones. So it's easy to interconvert between flying and stationary qubits, and it's easy to send these qubits from one place to another. But of course, the biggest disadvantage excuse me, of optical quantum computing is that photons don't like to interact with each other. I mean, if you shine 2 flashlights, you can see, through each other. You can see that the light just goes through. There's not really any interaction. And so it's really problematic to perform entangling 2 qubit gates. Okay, so let's look at. So for single photons, I don't know if I want to start that somewhere else. Actually, yeah, I'll start a new. So for single photons, it's typical to use 2 different types of encoding, and I believe Daniel mentioned them a couple of days ago. So one of them is called the dual rail encoding. And the other one is known as the polarization encoding. So in the dual rail encoding, we have 2 different spatial modes, A and B. And so typically, we represent these as, in the same way that we had circuit diagrams here, these optical interferometers look very much just like these quantum circuits. So we have these qubits flying from left to right. Excuse me. And actually, maybe I don't want to say that yet. Okay, so we have qubits going from left to right, and one qubit state can be having a photon in this mode, and no photon in that mode, and then the other one could be having a photon in that mode, but no photon in that mode. So we can write that as logical 0 looks like that, and logical 1 has the single photon in the other mode. Okay, and so now we want to do single qubit operations on these things. And they're pretty simple. We just use linear optical elements. So we can use something that's called a phase shifter. So let's say we put this element here. And so that's just going to be a transparent piece of material that has a different refractive index from air, for example. And so it's going to change the phase. And so then you can see that the effect of this material is going to be to do nothing on the logical qubit, 0, because it's not sitting in the A mode, but then it gives us a phase shift on the logical 1 qubit. So this allows us to rotate things on the Bloch sphere around the z-axis. Okay, then the other optical element that we use is a beam splitter. So let's say we have our 2 modes A and B, and we can get them to cross on a beam splitter. And we can parameterize this beam splitter by well, we can parameterize its reflectivity by a parameter theta, and then also we can include some phase elements that we can either directly embed into the beam splitter, or we can kind of control them by having some additional phase shifters. So in general, we can write down the transformation for this as so 0 goes to cosine theta, 0 plus I e to the I phi sine theta, and 1 goes to I e to the I phi sine theta, 0 plus cosine theta 1. And so if we look at the block sphere, then the value of theta is going to determine how much we rotate by. And then this value phi is going to determine the axis in this xy plane, which we're going to rotate about. So using these in combination with phase shifters, we can then implement all of the unitary operations. Okay, so then what happens with polarization? Well, in polarization, we have one spatial mode, but we have two polarization modes. And I'll just call them XY to be general. And so then our qubits look like this. So it's somewhat analogous to the other case. And typically, just for shorthand notation, we would write something like that. So you may have seen things like if X and Y were horizontal and vertical polarizations, you may have seen states like H and V, or diagonal and anti-diagonal, or right and left. So these are all common types of polarization states you may have seen. Okay, and then if we want to perform single qubit operations on these, we use an optical element called a phase plate, a wave plate, sorry. So that's just a piece of birefringent material, which can also be parameterized by the parameters theta and phi. So here, theta is determined by the width of this material. So as you know, let's say H and V go through this material, one of them gets delayed, and that's what gives you the phase between the two. And so then the longer the material is, the more phase delay you get. And then this parameter phi is just determined by, how you actually rotate the actual optical element. And I won't bother writing it down, but the effect on the logical qubits is just going to be exactly the same as we have here. Okay, and so they're pretty much analogous encodings, but sometimes it might be easier to use one encoding experimentally, and sometimes it might be easier to use another one. And you can very easily just interconvert between these two. And so let's say if we have some sort of polarization encoded qubit, so we've got, let's say, a alpha H plus beta V. And then we send it through what's known as a polarized beam splitter. So it's similar to a beam splitter, except that what it does now is that it, let's say, reflects vertical light and transmits horizontal light. So then you can see that if that's H and that's V, then this polarization encoded qubit is now going to be encoded in the spatial modes here. And then you can do whatever experiment you want to do. And then to get it back into, into a polarization qubit, you just pass it through like another beam splitter. So these two things are pretty much equivalent. Okay. Okay, so we have single qubit gates. That's nice. We also would like to do measurements. So measurements are quite simple, assuming that you have devices that can count the number of photons. Unfortunately, at optical frequencies, we have pretty good photon counters now. I mean, the best ones need to be cryogenically, cooled and stuff, but they have efficiencies of like 90-something%, which wasn't the case when I started like 10 years ago. The efficiencies were really low, like 40% or something. So a lot of progress has been made. Okay, so for measurement, we use photon counting. So in dual rail, we have, well, okay, so we're going to have A and B, and all we do is just stick, a detector here and a detector there. And if it goes click, then, we know that there's a single photon there. And similarly for polarization, we have just one spatial mode, and then we're going to split it up on a polarizing beam splitter and put detectors here, and then wait for one of them to go click.
So this means that you have to run both, but you have to know when the photon is the window time is the photon.
Right, yeah.
And then you look, say, either A clicks, B clicks, so we got error.
Yep. Okay. Okay, so that's what have we got? Single qubit rotations, measurements. The next thing would be to talk about entangling gates, but I'm not going to do that yet because I wanted to spend a little bit of time talking about the actual sources that we use to create the single photons. So kind of here I've assumed that we have them, but it's a little bit tricky to actually create them. Okay, so single photon sources. So ideally what we would like, we want it to be on demand. So it'd be great if you could just press a button and have a photon come out. We want it to be efficient. Meaning that it comes out when we tell it to. Not in any complexity class or efficient. Just.
So what's the difference between on demand?
Well, I can. So what I'll talk about in a minute will be. So you can imagine having a source that's efficient but not on demand. But how would I?
So it produces a lot of photons, but not necessarily.
Right. Yeah. You want it to be robust. So you don't want to, you don't want to have a situation where you sneeze in the lab and suddenly it stops working. And of course, you want it to be easy to implement. And so these don't exist. Right. Oh, but if they had them, imagine all the cool things they could do. They could have even better jobs. Okay, so there are a couple of common sources. There are single molecules or quantum dots, and these things emit a photon when stimulated by some laser light, or maybe stimulated by some sort of electrical current. They have their own issues, and I guess I won't really go into them. One obvious one, I think, would be that they're not really easy to implement. I'm not exactly sure how efficient they are. But the most common source that I'm more familiar with is what's known as spontaneous parametric downconversion. So, and this, that's not what I wanted to write, but okay. Spontaneous. So this particular source is like the workhorse of most of the quantum optics experiments and quantum computing experiments. Okay, so I've talked a little bit about it in some other lectures, but I'll remind you how this works. So, it's a nice source. It's not on demand, but it's heralded in the sense that it doesn't always produce a photon, but when it does, we know that it's there, and so then we can go ahead with our experiment. Do you have your hand up? Yep.
Can you repeat what robust means?
That it just doesn't break, like it continues to work, and so you could imagine things that are finicky. Like in principle, it's on demand and it's efficient, but as soon as the air conditioning in the lab changes slightly, it stops working or something. So you just want to. Well, I mean, there are different degrees of robustness, I guess. I mean, like, okay, so if you have, what was it? I was visiting Mike Mosca in his office, and he had like a little optical table with some, I can't remember exactly what the experiment he was showing, but it was some sort of typical experiment. And apparently they like unplugged it and then like plugged it in like a year later, and it like still worked. Everything was lined up, so that's pretty robust. Like an optical table is quite robust. So I don't know who asked that question, but yeah.
So when you say they don't exist, you mean is that a statement about our current
exactly
technology?
Exactly.
Or is there, so it's not fundamental?
It's not fundamental. No. And yeah. So ideally, I don't mean ideally in like the theoretical sense. I just mean that would be great if we could have that. But at the moment, we have different photon sources that satisfy different criteria, but they don't satisfy all of these. Okay, so this is this source. It's not on demand, but it's heralded. But it can be made quite efficient. It can be made robust. And it's pretty easy to implement. Like, people in an undergraduate lab could set something up like this. Okay, so the way that it works is we get a nonlinear crystal, excuse me, which has what's called a chi-2 nonlinearity. So chi-2 nonlinearity is nonlinearities that allow 3 modes to interact with each other. Later on, I'll mention chi-3 nonlinearities, which allow 4 modes to interact with each other. So in this case, we can write down the Hamiltonian for this. And I'll define what all the subscripts mean in a second. But you can kind of infer what is happening here, that it's going to destroy 1 photon and create 2 photons, or it'll create 1 photon and destroy 2 photons. So we get a crystal with this particular Hamiltonian, and then we shine a very strong laser at this crystal. So it's got a subscript P because we usually refer to this as a pump. So we have a laser of frequency omega P, and most of the time it'll just go through and nothing will happen. But sometimes, with some probability, one of the photons in this pump is going to split into a pair of photons. So you can set things up so that they go off in two different directions. And so there will be photons of frequency omega 1 and omega 2, and they're going to satisfy energy conservation and also momentum conservation. And so that's why they're going off in different directions.
How can you guarantee that, like, that they're going to go off in the same direction every time? Like, it's the angle that makes the omega 1 makes with the normal.
So this thing has some. This crystal has a particular crystal structure,
Right.
and so it's phase matched only, so that the things come out in a particular direction. But I'll mention a little bit later. You can change things, like you can cut the crystal in a different way, and so by doing that, you can change the angle of this cone, and so you can get them to all come out in the same direction. But for the purposes of creating single photon sources, you want them to be going off in different directions. And I mean, you can do things like also, change the direction of this angle and so on, so you have some control over that. Okay. So we have something that happens like this, but it's a spontaneous process, and it happens probabilistically. So yes.
Is there any kind of control on the output wavelengths, or are they just random?
No. Yeah. So I wasn't going to go into that much detail, but there's definitely control over it. So I mean, this is a very simplified picture, but you can describe the spectra of the two photons that come out, and typically you have to describe it by what's known as a joint spectral distribution. So you can't just control, have separable spectra, and so they're going to be entangled in frequency. And so typically, like if you wanted to draw these things, they look something like, they have these funny shapes. And so this is like frequency omega 1 and omega 2. And the properties of this joint spectrum depend on things like the spectrum of the input pulse. So if it's got, some sort of Gaussian pulse, you get some sort of Gaussian distribution along here. And then the properties of the joint spectrum in this direction depend on the Fourier transform of the nonlinearity profile of this crystal. So there are things that you can have experimental control over. Yeah. And you can do lots of really interesting things with that. Sorry. Yeah.
Is there a reason we can treat this as, like, since we can say with some probability that a pulse goes through, with some probability that it splits, can we use that as, like, a 0 and 1 state?
Not so much, and I'll show you in a second why. So I'll answer that question in a second. So what I was about to get at was, because this process is spontaneous, it's possible that sometimes it doesn't happen, but it's also possible that sometimes it happens twice. So you can get two photons splitting up into two pairs of photons, so you get 4. And so you can actually write down the entire state that comes out. And it's going to be a superposition. Okay, so let's say we're working in a regime where these two photons are going to have different polarizations. So that's known as type 2 down conversion. So with some high probability, you're going to get the vacuum state out in both modes. And then with a lower probability, you get a pair of photons coming out. And then with an even lower probability, you get 2 pairs. And so on, and this goes on forever. And so this parameter lambda It depends on the strength of the laser that you have, and it also depends on how long your crystal is. And so these are things that we have control over. And so if you have a state like that, it would be quite difficult to turn that into a 0+1 state, because you'd have to like trace out or get rid of one of these modes. Maybe somehow if you could like make a measurement on one of the modes that projects onto 0+1, then the other one would be projected into 0+1 as well. Okay, so you have a state like that, but what you really would like is a single photon. So to get a single photon state, what you do is you put a detector here, and you wait for that detector to go click, and when it does that, that's your heralding that says you have a single photon in this mode, and then you send this single photon through your optical experiment.
And so 2 questions.
Yes.
Firstly, the detectors are good enough for the color difference between 1 and 2.
Yeah, so in the early days, people used to work in like a really low pump regime where it was almost impossible for you to get these higher order modes, higher order terms. And so then you didn't really need photon number resolving detectors. But these days, they're because they want to make these photon sources more efficient, they have to pump them harder. And then you really want to be able to discriminate between the photon numbers.
Second question.
But they do have detectors that do that with some efficiency.
I want to make 2 qubits now.
Yeah, I'm about to show you how to do that. Yeah. Yeah. So the cool thing about down conversion is it's really, really versatile. You can, depending on how you set things up, you can make all sorts of different types of states. Later on, I'll mention cat states. So you can use down conversion to create approximations to cat states. You can use it to make squeeze states, which I'll also briefly mention later. And yeah, you can also use it to create bell pairs, which I'll show you how to do now. Okay, so that's how you get the single photon source. But if we want entangled pairs, we have to change the experiment a little bit. So one thing I didn't tell you is I drew this simplified picture like that. But really what's happening is that this comes out in like a cone. So it's like this symmetric cone. And so this H photon is correlated with that H photon, that V photon. But really you kind of have these two H and V cones on top of each other. So then you have, this guy correlated with that guy correlated with that guy. And so, they're kind of all entangled around here. And so what you can do is you can cut the crystal differently so that it splits these two cones up. So, the horizontal cone goes up and the vertical cone goes down. And so you have a situation like you've got the pump coming in here. And then you have your horizontal cone coming out like that. And your vertical cone coming out like that. Maybe I'll draw it. And so now the correlations are slightly different. So like this guy is going to be correlated with that guy. This one here will be correlated with that one there. So as long as they just all satisfy energy conservation. And so the place that we're interested in is the place exactly where they intersect each other. And so as long as everything's done coherently and you've maintained all the phase relationships and everything, then when you pick out a pair of photons from here, you don't know whether that photon was horizontal and that one was vertical, or that one was vertical and that one was horizontal. So it could have come from either of the two rings. So then the state that you create is a state that looks like this. So that's your entangled bell pair.
How do you herald that?
Pardon me?
How do you herald?
You don't herald it. So typically what happens is you go ahead and do your experiment and you assume, you send whatever comes out, you send it through your experiment, and then at the very end you post-select on having you can do what's called coincidence counting. So you just make sure that you're always just detecting a pair of photons that are correlated in the appropriate manner, like that they came at the same time. So you can use excuse me, you can use this source for doing proof of principle experiments to show that your gate works in principle. But I don't think you can actually use it to implement a quantum computation, like anything useful.
So like if I was to run an experiment like this, I want to produce a bell pair, do some kind of measurement on it, and detect at the end. Am I going to be able to leave this for like a minute and then find the field that come through, or am I going to be waiting hours?
No, so this is kind of one of the original proposals. Like they've since then improved. So there are ones that kind of use two slices that are 90 degrees away from each other, rotated from each other. And I mean, they're very efficient. Like, I mean, it could be, I'm going to make up a number, but it could be like 1 million a second or something. Like there's a lot of them happening, yeah. I mean, it might be a bit less, but it's kind of that sort of within a few orders of magnitude. Okay. So these things are entangled states, and we're going to use them as resources later on for other things as well. Okay, so I mentioned photons don't like to interact with each other. And even though we can create entangled pairs, what we really want is to be able to entangle two pairs that already exist, so that we can do some sort of operation. So one way to do it is to use a nonlinear crystal. And so here I was talking about a Chi-2 nonlinearity that relates 3 photons with each other. But in order to make 2 photons come in and 2 photons come out, you want something that has a relationship between 4 different photons. So we want to use a higher order nonlinearity, so what's called a Chi-3 nonlinearity. So this is an effect that's called the cross-Kerr effect. And the Hamiltonian for that is going to be where these are the number operators that were defined before as A dagger A. And what this does is it induces a phase shift on the light that depends on the number of photons in the state. So, hang on, we'll try that. Induces number dependent phase shift. So if you have some sort of state and you apply the unitary operator associated with that Hamiltonian, then you can see it's just going to pull out the number of whatever that state is, and it'll give you a phase shift that depends on this number. Okay, so if we want to do an entangling gate, what we have, let's say we have our 2 polarization encoded qubits. We're going to split them up into path encoded qubits. So let's say that's H and that's V. And then we're going to send these things through one of these Chi-3 crystals. Okay. So let's just write down the possible states. Okay, so it should kind of be clear that the only time that you're going to get a phase shift here is if we have 2 photons in this mode, because we'll get something that's e to the I kappa t n, like where n is 1, and n again when n is 2. While if there's 0 photons in any one of these modes, then that thing in exponential is going to be a 0, so you're going to get a 1. And if both.
This chi3 getting influenced across.
Yep.
Okay.
Although somehow using that argument, I'm missing a factor of 2. But it's effectively something like this. And so, yeah, I'm going to need to go back and check where this factor of 2 came from. Okay, so all of these states are unchanged, and then you get this phase shift here.
How do you get like correlated states in the beginning to? I mean, so like personally, it seems to me to do this, do you need to have your photons like correlated states so that they're coherent instead of correlated, or can they be decoherent?
You need them to both be going through here at the same time.
Right. How do you organize? How do you, given that the sources are like, kind of.
Right. Okay. So, like if you've got 2 probabilistic sources, then and let's say it creates a photon with probability p, then you're just going to be sitting there and waiting for something that works with probability p squared. Like it'll just work less often. But I mean, that's just the price you pay when you do multi-photon experiments using these sources.
So there's some kind of like time window that has to overlap.
Yeah. If one of them goes through and leaves before this one comes in, then it's not going to give you the right nonlinearity. But it doesn't matter because this doesn't work anyway. Because to do something useful like a C phase gate, we want this thing to be a minus. So we want kappa t to be equal to pi on 2. At the moment, the largest Kerr medium is extremely weak. So now we have things like kappa t is equal to 10 to the minus 18. So I'm going to not even get to superconducting qubits, unfortunately, because I've run out of time. And that's actually more interesting than this. Anyway. Yeah, so pretty much like knowing this, like nobody thought that optical quantum computing was ever going to really work until this very famous paper came out in 2001 by Neil Laflamme and Milburn. So Manny Neil and Ray Laflamme, they were in New Mexico at the time, but now Ray, you may know as the director of IQC. And Jared Milburn, you would know he's a professor at our home university. The KLM gate, right. So Neil Laflamme, Milburn stands for KLM. And so this is pretty much the thing that started the field of linear optical quantum computing. Okay. So fortunately, we got KLM. And so I'm going to describe KLM, well, a little bit about it right now. So the actual KLM paper, it had 3 important bits in it. The first one was that they showed us how we could make non-deterministic entangling gates. Using linear optics. Non-deterministic. The second bit was that that we can increase this probability of success arbitrarily close to 1. And so we do, well, let me write that down. And so this is done by using entangled states as a resource. So these are the states that we're able to create using down conversion, and also using tricks that involve teleportation. So Daniel, a couple of days ago, talked about teleportation and how it can be useful to do certain things. So one useful thing is, well, in this case, for increasing the probability of success of these gates. But this is extremely resource demanding. Like, it does not scale efficiently at all. So then the third thing that they did was that we can use, well, they showed that you can use quantum coding to make this thing resource efficient. And so in this case, what resource efficient means that the number of resources scales at most polynomially with the complexity of the computation. And so I think in this paper they actually showed that it scales linearly. So that was great. But I'm not going to talk about 2 and 3 because it's kind of outside of my area of expertise. And we're going to learn about quantum codes later on anyway. So what I wanted to show you was how you would actually implement this non-deterministic gate. Okay, so okay, so there have been quite a few different realizations of this gate. I'm going to talk about the one that was done in Queensland because I'm going to support my people. So this was done in Andrew White's group. I actually think it's also one of the easier ones to understand, but maybe just because I saw it a long time ago. Okay, so this is a paper by Jeremy O'Brien, Jeff Pride, and a whole bunch of other people. And so the way it works is, actually, let me just try and draw it first, and then I'll describe it. Okay, I practiced this. Okay, so it looks something like this. So what we have is our path encoded qubits coming in. So you can say that this is like HV, BH or something. If they started off as polarization ones, it would be split up into these paths. Okay. So in the case of, and all of these are beam splitters. With reflectivities of a half and a third. And implicit in here are mirrors, that send these, reflect these modes. And so, okay, if in the case where the input is, let's call it a 0, so that means that the photon is in this mode. So we've got our control being a 0. Then it doesn't even interact with the target qubit at all, so it passes through. And then in that case, this whole thing here is going to be just a symmetric interferometer. So ignoring, let's say for the moment we ignore these beam splitters, then you would imagine that if a photon comes in here, in the target being 0, it'll just be reflected out here, so it doesn't change. And if the target is a 1, then it comes through here, and it doesn't change. So we get that sort of behavior. So 0, 0 just goes to 0, 0, and 0, 1 goes to 0, 1. But of course, we have these beam splitters here. And so occasionally, the photon might be transmitted. So actually, 2/3 of the time, it'll be transmitted and come out here. Or it'll be transmitted here and come out here. And in that case, then the gate fails. So we only consider the gate succeeding if we detect one photon in this mode and one photon in that mode. Otherwise, the gate fails. So you can already see here that it's going to be failing 1 minus 1/3 squared of the time. So 8/9 of the time it's going to fail. And now in the case where our control qubit is a 1, then we have a photon in this mode. It'll interfere with the photons here. And what it does is it induces a pi phase shift on the top mode. And so then things interfere in a different way. And if a photon comes in here, it interferes in such a way that it comes out from this port here. And vice versa, if it comes in here, then it comes out the top. And so we get the flip. And so in the tutorial, we're actually going to go through this interferometer in detail so you can understand how it works. And so this gate, because of these loss modes that are necessary to make everything come out symmetric, that it only works while it succeeds 1/9 of the time. But fortunately, using parts 2 and 3 of the KLM paper, there are tricks that we can use to make this work with high probability and doing that efficiently with resources. So I think the last thing I'm just going to say about this is that, okay, so even though number 3 tells us that it becomes resource efficient, the number of resources is still huge. Like, it's really big. And so if you're going to be, I mean, I don't know, I guess you guys have visited the labs at IQC. Like, these optical tables are really big. And so, like one gate can be half an optical table. And so even if the thing scales linearly, like you really don't want to be building these things on an optical table. And so one of the recent, like in the last 5 years or so, one of the technological advances that we've had comes from Jeremy O'Brien's group in Bristol University. So it's the same guy that, as a postdoc, worked on this gate. And so what they do is they make optical integrated circuits. And so these things So these circuits consist of, like, they're kind of tiny, and they're these little blocks of silica. So imagine something like that. And then in this little block, they write these waveguides, which kind of look like that. And so the way they build them is they kind of make this, they grow some silica, and then, like, they grow that much silica, and then they grow just something that corresponds to the waveguide out of a doped silica, and then again put some more silica on top of it. And so then they get, the light kind of comes in and then just gets guided by these modes. And so now, instead of having a beam splitter like this, they control how much coupling there is between the modes just by bringing them closely together, and then they couple through what's called evanescent coupling. So the light kind of leaks out of each mode, and then the two leaked bits interfere with each other. And so it's possible with some probability for the light to go from here and then come out this mode. And so then the corresponding integrated circuit that looks like this would be something like that. like this. It kind of looks like a mess. And so these would be the two control qubits. These would be the target qubits, and then you have some additional vacuum modes. So you're not going to be putting anything in there, but it's possible that light comes out here. And then you detect here. And so these things are really tiny, like, you know, you can get a C naught on something that's, you know, maybe like smaller than a centimeter instead of something that's like the size of an optical table. So that's pretty neat.
They're trying to build
Pardon me?
quantum microchips, right?
Yeah, yeah, but optical ones.
They work?
Depends what you mean by what.
So no, what?
Could it ever depend what we mean by work?
I mean, they're demonstrating things that have been demonstrated on like in optical, in bulk optics.
Yeah,
I mean,
this
like,
is like, I mean, this seems like the first step to
yeah.
build
So,
a computer that you could actually use.
so I think that, I mean, I haven't been following it too much recently, but I think that the actual waveguides are pretty good. Like, they've got the fabrication down pretty well. But then, like, what they want to do is actually put, you know, nonlinear material inside the waveguide so that they can create single photon sources inside rather than having to use, you know, parametric down conversion outside and then try and couple that into the waveguide. So they're trying to put all of the components, like, into the actual,
Do you know
the thing.
when they started doing this?
2008. Yeah.
Within 7 years.
So when do I get a quantum microchip?
Oh my God, it's 2015. I was like, oh, 3 years ago.
When do I get a coupon?
So I had quite a lot of other stuff that I wanted to talk about. I wanted to tell you about
I'm gonna patent it.
continuous variables. And like, I really wanted to talk about superconducting qubits. So maybe, I don't know, like maybe we can, in the tutorial, I can like spend half an hour telling you about that. Because it's like, it's really, really interesting. And yeah, then the rest of the tutorial, we can do the actual questions. Okay, so I'll see you at 3:45.